you for the kind introduction, and thank you all for coming. So today I will be presenting a seminal paper in the bin packing literature. It's called Bin Packing Can Be Solved Within 1 plus epsilon in Linear Time by Fernandez, Vega, and Lueker. Oh, yeah. I was just planning on running back and forth to click. There's going to be a lot of clicks. So, thank you. Yeah, click, please. Okay, so let me just introduce the problem of bin packing. Click, please. Bin packing is an optimization problem in theoretical computer science. There are items of different sizes that must be packed into a finite number of bins of fixed capacity. But in this talk, we will have all of the bins have capacity 1. And we must do this, or we want to do this in a way that minimizes the number of bins used. So we're given a list of item sizes and bin capacity of 1, and we can open as many bins as we need. And what we want to do is we want to minimize the number of bins used, K. And we want to make I into K disjoint sets so that each I sub J goes into a separate bin. And no bin is over its capacity. So bin packing is a very studied problem because it has many applications such as resource allocation, memory management, and logistics such as shipping and filling up containers and loading trucks. So we're gonna give an example of bin packing. So in this example, we have 5 items of sizes 0.2, 0.4, 0.5, 0.6, and 0.3. And each bin has a capacity of 1. And an optimal packing is shown there using 2 bins. The first bin housing the items of weights 0.2, 0.5, and 0.3, and the second bin housing the items of size 0.4 and 0.6. Can you think of the simplest greedy algorithm you can? So I'm not sure how much audience involvement there is in this kind of event, but does anyone want to give the simplest greedy algorithm you could come up with? It doesn't have to be optimal. Yes.
Just find the first bin that that fits. Just throw it in there and iterate.
Yeah, exactly. So this is called the first fit algorithm. You keep a list of open bins, which are initially empty. And when a new item arrives, you just find the first open bin that can fit it. If there is no such bin that can fit it, then you just open a new bin and put it in there. This one's going to have a lot of information, so you can't press it all at once. I think I can control this slide. Okay, so let's run through a first fit algorithm. Shown here is the same list of items we had on the last slide. So number 1, you're shown item 0.2 first. So there, but you have no open bin available yet, so you open up a new bin for it. And then the next item is 0.4. Is there a space for 0.4 in the first bin? Yes, there is, so you put it there. But then next you see 0.5. 0.5 does not fit into the first bin because it will make it go to 1.1. So you open up a new bin for it. And then 0.6, is there space in either of the first 2 bins for it? There's not. So you open up a new bin for it. And then 0.3, does it fit into the first open bin, which is the one housing 0.2 and 0.4? Yes, it does, because it would only make it go up to 0.9. Okay, so this is the first fit result. You end up with 3 bins. But then remember that the optimal was 2 bins shown on the last slide. So first fit is not the most optimal algorithm. I think you can go back. So can you think of a polynomial-time algorithm that gives you the correct or the optimal answer? Click. If you can win $1 million. So unfortunately, P equals bin packing is a polynomial. It's an NP-complete problem. And P equals NP is a Millennium Prize problem. So, for previous slide, sorry. Yeah, so it's very likely that there is no polynomial time algorithm for bin packing that gives it the optimal answer. So what can we do in this case then if we cannot most likely have a polynomial time optimal algorithm? So we can do something called approximation algorithms. So we want to talk about now the approximation ratio of the first fit greedy algorithm we just discussed. And what does that mean? Some notation. First fit of L means the number of bins used by the first fit algorithm on the input list L. And then opt of L means the minimum or the optimal number of bins used by the optimal, a supposed optimal algorithm. First fit was proven to have the following approximation ratio by Ullman in, I think, 1971. And it was later improved to be just the floor of 1.7 times opt. So what this means, what does the 1.7 mean? It means that the number of bins output by the first fit algorithm is at most 1.7 times the number of bins by a supposed ideal optimal algorithm. So some notation if we're not familiar, the following are floor and ceiling functions, which just means rounding down or up to the nearest integer. So if the feet or the serif are below the bars as a floor function or rounding down function, and the other way around is the rounding up function. So now we want to talk about why the Vega and Lueker algorithm is important, the paper I'm presenting today. So this paper showed for the first time that for every positive epsilon, no matter how small epsilon is, could be 0.4, 0.1, 0.002, there exists a linear time algorithm for the bin packing problem. And you can get an approximation ratio of 1 epsilon, which can be really close to 1. So once again, what does that mean? It means the number of bins used by this algorithm divided by the number of bins used by an optimal algorithm is at most 1 epsilon. Any questions so far? Okay. So what are some key concepts of this paper's algorithm? So there are two key concepts. One is adaptive rounding, which is something that was introduced in this paper. This paper invented adaptive rounding, which involves reducing a problem instance to be a manageable size by limiting the number of distinct item sizes. So that means rounding each item size to be the nearest multiple of a number, or putting each number into a separate bucket and assigning the same number to every number in a bucket. And then the next key concept is using a restricted problem, meaning solving a simplified version or a subproblem where item sizes are within a manageable range as opposed to the whole range of the given problem. So let's talk about the second point, solving a restricted problem. What if we were given a simpler problem? That means if all the items that we have to put into bins were from the range of eta to 1, where eta is some real number between 0 and 1. So, for example, if we were given items of sizes 0.1, 0.2, 0.3, 0.4, all the way up to 0.9, and we set eta to 0.4. That means we only want the items of size 0.4 or greater. And then the other factor here is there are only m distinct item sizes. So meaning the granularity of the input is not as fine. So how would you solve it? Or if you cannot think that up right now, do you think it would at least be easier than solving the full problem? So yes, it is easier to solve or approximately solve a restricted problem for bin packing. So we want to introduce configuration LP, which is actually a concept not introduced in this paper. It was introduced a few decades prior for the stock cutting problem. So in a configuration LP, does everyone here know about linear programs? Or heard about linear programs? Okay, so basically, that's fine. Linear program is you want to maximize or minimize a mathematical expression subject to certain constraints. We'll see in a minute. So, but in a configuration LP, it's a specific type of linear program. Instead of just instead of having any type of constraint or objective, you want to work with configurations, which in this case means possible configurations of bins or possible combinations of items that fit into a single bin. And we will give an example here. So for example, if the bin packing instance were 33333, 44444, and the bin capacity is 12, then some ways that you can pack a bin are putting 4 threes in, or putting 3 threes in, or 2 threes, or 1 3. All of these each of these lists can fit into a bin of size 12, obviously. And so it's true for the remaining lists, because as you can see, 3 plus 3 plus 4 is 6 plus 4 is 10, and the sum of each of these lists does not exceed 12. So each of these is called a configuration, or a bin configuration. Okay, so we want to talk about the variables or notation used here because it's a lot. So Q is the number of configurations. So if we want to go back to the previous slide, thank you. The previous slide, Q would be 10 because there's 10 possible. Am I counting right? The 10 list? Yeah, there will be Q would be 10 in this case. And then M would be number of distinct items, which for the previous slide, M would equal 2 because there's only items of size 3 or 4. And AI would be, A sub I is a variable, meaning we don't know what it is yet. We will let the computer figure that out after plugging this program into the computer. And A sub I represents the number of bins of configuration I. And then T sub I comma J is the number of occurrences of size J in configuration I. So for example, if we go back, thank you. So let's look at the first list here, 3333, the number of occurrences of 3 in that list, in the first list, equals 4. So T sub number of, so 3 occurs 4 times and 4 occurs 0 times in the first list. Whereas for the last list, 4 occurs 3 times and 3 occurs 0 times. Yeah, no, okay. And then lastly, N sub J means the number of items of size of item J. And that sounds a bit complicated. It's not the number of items of item J, it's the number of items of the size of item J. But let's consider it all in the context of this configuration LP. So because we want to minimize the number of bins used, we set our objective to the sum of all a sub i's, meaning you want to minimize the number of bins of all configurations used. So that's the objective up there. And then you have two constraints here. Number one is you want to ensure that all items are covered by the result of the LP. And number two, you want to make sure that the objective is not negative. Because if you minimize the objective, it can go into negative infinity, but you don't want that. So that's basically what these two constraints are. The first constraint, a sub I times t sub I comma j, that's number of bins with configuration I multiplied by number of occurrences of size j in configuration I. So I'll just give you a minute to digest the LP. Yeah. Okay. So now that we have plugged this LP in this linear program into a computer, and there are many linear program solvers out there available, by the way, so that's not the hard part. So let's say the computer now spits back all the a sub i's. So we have an intermediate answer right now. How do we use these a sub i's to get a solution for bin packing? So the computer.
I think I have to speak up.
Okay. Okay, so now that the computer has given us each a sub I, how do we use it to convert to an actual answer for our bin packing instance? So first, note that a sub I, they're real numbers, meaning they could be decimals. They could be like 2.1 or 3.45. But in real life, you can't open up half of a bin, right? You either you use a bin or you don't. So what you do is you round up each a sub I to become a sub I prime. And there we see the ceiling function again. It just means rounding it up to the nearest integer. And then you can use these a sub I primes to construct your answer. Meaning if a sub 5 equals 6, that means you have to use 6 bins that have configuration number 5. And notice that because we're rounding stuff up, some items may be unnecessarily repeated. Meaning represented more times than in the original problem instance. So what do we do here? That's not a problem. You just take out the items that are represented more times than they should be. Yeah. Okay, so how good is this LP solution after the rounding compared to the optimal answer? So there's one more to click. Yeah, so it's an additive factor of error, and the additive factor is Q, which is the number of configurations. And why is that? So when you round up each a sub I, that means you're rounding up a variable for a type of configuration. And because you're rounding up each you're rounding up each number by up to the next to the next integer, the most you're adding to your answer is Q. And that's that is our additive factor. So yeah, okay. And then how efficient is running this configuration LP? So first we want to upper bound the number of possible bin configurations. So we saw earlier that 33333 and 4444 in the problem instance gave us around 10 configurations. So what if we have an arbitrary number of distinct item sizes and arbitrary number of bits, for example? So that we can calculate that by getting n plus k choose k. And this is from the stars and bars theorem, which is for figuring out how many ways you can choose m plus one non-negative integers that add up to k. And the way you can visualize this is think of each positive integer as a separate star. And what you're doing, what you want to do is you want to put up bars between these stars so that eventually, so that this represents an addition problem, meaning, thank you. So you can visualize this problem as putting bars between stars. So if you put a bar, if you put two bars around three stars, that means one of the numbers you chose is 3, and so on and so forth. And this is a classic combinatorial problem. So that's how you upper bound the number of constraints and variables in the linear program. And notice that in this bound, n does not appear. So the number of items does not appear. This bound only depends on eta and m. And remember, eta was the lower bound of item sizes. So it could be 2.2 or 0.4 and so on. And m is the number of distinct item sizes. So now that we have figured out how to approximate a restricted instance of bin packing, how do we use it to solve the general non-restricted case of bin packing? So we want to partially reduce it to the restricted case. And the brief overview is that given a non-restricted instance of bin packing whose items are given in the list L, you want to find the subinstance comprised of only a portion, L prime, of the original list. And then you make the configuration LP we just discussed from it. And then you put that LP into an LP solver in, say, Python or wherever in your computer. You get the vector back, and then you get your approximate solution from it. And then for the rest of the items, you put them into the remaining space in the bins. So that's the overview of how to solve this problem generally using the restricted case talked about before. Okay, so in more detail, how do we do that? So first you pick an eta, which is the floor or the lower bound of the numbers you want to put into the LP. And all items of size greater than or equal to eta are from now called big items. And then you want to sort all the big items, and then you want to put all these big items into buckets of almost equal cardinality. You want to put them into n buckets. And then you want to do the adaptive input rounding step, which is rounding each of the numbers in the buckets to its biggest item, to the biggest item in its bucket. So now you have very few unique item sizes because you've made every single item in a bucket into one number. And then now you want to run the configuration LP on these big items after you reduced their granularity. And then now you want to put the small items in. So after you put the big items into their bins, you want to put the small items into the remaining leftover space. Yeah. Okay. Now, how efficient is the Vega algorithm or the runtime? So recall that we said earlier the number of variables and number of constraints in the linear program depend not on n, the number of items, but rather on eta and m. And recall that eta and m, because of how we did our rounding and our bucketing, depend only on epsilon, which is a constant that we choose. And you might be thinking, well, didn't you mention a sorting step earlier, and the sorting can only be done at best at O and log n? Well, actually, for the sake of simplicity, I said sorting, but you didn't actually need to do sorting. Due to Blum et al. In 1973, you can find the kth largest element of a list of length n in linear time, in O of n time. So you did not actually need to sort in order to do the bucketing step. So now this algorithm overall is linear time. And it is an additive approximation algorithm. And this paper is considered very important in the history of, in theoretical computer science. A lot of papers later on either adapt ideas from it or, yes, adapt ideas from it and cite it. So Gupta and Pei used it for a paper on graph matchings, for dynamic graph matchings. And then one of my papers also cited it, or used it for bipartite maximum matching. And then these later two papers are also graph problem papers. One is for graph partitioning, meaning you want to partition the nodes of a graph for various objectives. And then the last one is for finding graph spanners. And these are all the references I used, all the papers I cited during the talk. Any questions? Come here.
My raise of hands. No one denied.
Yes.
So you said that this is not
Yes.
What is the actual
So what is the actual complexity of with the dependency on epsilon? Does it blow up a lot or?
Yes. So the devil is in the details. Yes. So one of the factors. So it's supposedly linear time O of n time, but because epsilon is a constant we chose, we just kind of hand wave that out. But one of the factors is log of 1 over epsilon, which could be pretty big. Yeah.
So I have a question. So you show this working for basically real numbers, so single dimensions. I'm wondering how the complexity of the algorithm changes when you take it to higher dimensions. So for example, packing boxes inside of a storage container.
Yeah. So actually this paper has an adaptation to the multidimensional case that I did not read, but I encourage you to do so. Yeah. Good question though.
And how does it change the complexity generally?
Generally, adding dimensions adds a lot more complexity to the problem, yes. Because you can always reduce higher dimensional problems to lower dimensional problems.
Is there a rough guess? Okay, thank you.
Is there a rough guess of where there's a trade-off between the first fit and this one?
The trade-off between this and first fit?
Well, I mean, in terms of O of n, in n.
Oh, of n. Well, yeah. So first fit is truly linear time. You just, you're given an item and you just search for the first bit that's open. Whereas this one, it's O of n, but with a caveat of log of 1 over epsilon.
I guess I'm saying is practically where you choose what. For small n we do this, for large n that, or.
Yeah. So if you're given an instance and you look at it and you see that there's not a lot of different distinct item sizes, then you should try this one for more optimality. But actually, first fit in many cases is already pretty good in reality. And with simple tweaks to first fit, like sorting the item sizes first, it decreases or improves the approximation ratio by quite a lot.
So following up on that, what are some cases where we want to use the bin packing you presented? Because you said that first fit was good for a lot of things. I just recall during one of my internships, I used to write this really bad program for matching basically food delivery to autonomous vehicles.
Uh-huh.
And all I did was first thing just throw it on the vehicle. So yeah, I was wondering the applications.
Yeah, first fit, well, okay, so for this one, it's much harder to turn into, to adapt it to an online setting, whereas first fit is used in many cases for the online setting where, items just come in streams. Like for example, Uber, all these dynamic allocation settings. First fit is in many cases pretty good. But if you have a bunch of offline, an offline instance, then this in many cases is better.
Any other questions? Cool, so I think.
So I think when you were speaking, you were saying that obviously because of linear time performance, but effectively the constant factors can be really large.
Sorry, I can't quite
So
hear you.
I think when you were speaking, you were saying effectively you have this linear time guarantee, but like the constant factors can be large influenced by epsilon and so on. I was wondering, either this problem or maybe the problems that your research and your paper addressed, what kind of classes of algorithms would one be looking at if you're looking at things that are competitive in practice, it's called, in contexts where this might not be?
Sorry, what kind of variables?
What kind of classes of algorithms come in as competitive in practice? So like, broadly in this space, like what algorithm classes are we looking at?
For bin packing?
Yeah.
I actually don't know. I haven't done I don't know. I haven't really done a logistics internship.
Okay.
But, yeah.
That's fine. Did anything like that come? You mentioned a paper of your own.
Actually,
How was that?
in many cases, if the number of variables is not too big, a lot of times people just run an integer program. Yeah, actually, in my internship right now, am I allowed to say? I have tried integer programming, but up to a certain point, it blows up and it becomes impractical. So you're pretty much forced to use a prox algorithm like here. But for fewer parameters, like a few hundred, and depending on how complicated the problem is, because there are many variations to bin packing, like you can do many sorts of fancy things to the items, to the cost, to the capacity, or whatever. Sometimes you can't really do an integer program. Yeah.
Okay.
Any other questions?
I was curious because you mentioned some research you did yourself.
Yeah.
It's a bipartite matching problem where you use adaptive rounding. How did it come up in that setting?
Okay, yeah, so in bipartite matching, you want to maximize the edge weights you have in your eventual matching. So one thing you can do is you can round up the edge weights. You can likewise put the edge weights into buckets so that there's fewer distinct edge weights. Yeah.
Okay. That's how it shows up fairly generally. Just taking some collection that can be continuous and then chopping it up.
Yeah.
Anybody else? All right, thank you so much for the presentation.
I had a thank you slide.
Here, I'll send them. Thank you again, everyone, for coming. And thank you so much to Espresso AI for hosting us. please go reach out to Ben or Alex if anything they're working on sounds interesting to you. We're going to be going to Kent Ale House, a couple-minute walk from here afterwards, and please help finish this wonderful amount of pizzas that we got here. The video recording will be posted, and please join the PapersWeLove Discord to stay up to date on the upcoming event. Again, thank you all for coming. Cheers.